All right, so we're doing Unit 6, Lesson 2, Part 2. We're going to continue with instantaneous rate of change. And we are going to use this approach. All right, finding instantaneous rate of change from an equation. Squeezing a preceding or following interval is a technique for estimating instantaneous rates of change. By finding average rates of change that get progressively smaller, you can make more accurate estimates as to what the rate of change is approaching for an exact point. So in this example, let's say we have, one moment, please. Here we go. Let's copy this. Wait. Okay. We have this nice little chart set up for us. And we're going to use this equation here, 2x cubed minus x at x equals 2. So remember, we're looking for the instantaneous rate of change at x equals 2. So we're going to use points that are close to 2. So the first interval is between 2 and 3. So plug in 3, plug in 2, find your y value, subtract them, take your x value, subtract them, and then you divide your difference in y over difference in x. So we get 37 for the first one. For the next one, remember, since 2 was already done, we know it's going to be minus 14. Because we already know when we substitute 2 into the equation, we get 14. And in this case, it's 2.5. So if I substitute 2.5 in, what do I get? I get 28.75. And then you subtract those two and you get 14.75. Here we have 2.5 minus 2, which is 0.5. And then you just do 14.75 divided by 0.5. And you'll get something close to 29.5. So see how the number has changed? Because we're going to get closer and closer to the actual instantaneous rate of change. Because the interval is too big. 2 and 3 is too big. 2 and 2.5 is still too big. So we're still going. And we're going to get, progressively smaller and smaller. So let's say 2 and 2.1. This is going to be, once again, minus 14. We already know what 2 is. Substitute 2.1, and you should get 16.422. Remember, I'm substituting 2.1 into this equation here. So 2.1 cubed times 2 minus 2.1. Once you do that, you should get this value. And here you're going to have 2.1 minus 2, which is 0.1. And here we have our value of 2.422 divided by 0.1. And you get something close to 24.22. See how the number is getting even smaller? And it's getting more closer to a certain value. Now we're going to do 2.01. So once again, 2.01 minus 2. This is going to be 0.01. And here you still have 2, so that's minus 14. And 2.01, if I substitute that into the equation, I should get something along this line. We want to keep, I'm not writing all the decimal places, but we want to keep as many decimal places as possible. So I'm going to write it here. 0.231202. And this is important. So when you're using a calculator, usually your calculator has a function that you can save an answer. So keep all the possible decimal values. All right, and this is our rate of change now when the interval is this small. And now we're going to just do one step smaller and do 2 and 2.0001. I may have said an extra 0, sorry. All right, so plug in that, and you should get something like 4.02, 3. And I'll write the full decimals in a bit. And this is going to be 0.001. And you should get 0.023012 divided by 0.001. And we get 23.012. So see what happened here? It went from 23.12 to 23.012. So it's getting closer and closer to a certain value. So it started from 37, then 29, then 24, then 23, and 23. So imagine if I were to do something like 2.00000, like infinite amount of zeros and then like 1. What would it be then? What value is it heading towards? And there's a pattern. It's getting smaller and smaller and closer to. We can assume, make it a good guess, educated guess, that's closer to 23. So the limit, as it's approaching 2, the secant, the slopes approach x equals 2, we can estimate the slope of the tangent to be 23 roughly. There you go.